Welcome, everyone. Thank you for joining us for today's presentation, Predicting System-Level Electromagnetic Noise and Immunity by Simulating using 3D FDTD Solver Technology with GPU Computing. My name is Srđan Đorđević, Application Engineering Architect at Cadence. I have over 25 years of experience in signal integrity, power integrity, EMC, and thermal analysis of the IC package and PCBs. I've been at Cadence since 2010, supporting customers in SI, PI, EMC thermal analysis of their IC package PCB systems. Today we will speak about design challenges in growth industries, automotive, consumer electronics, healthcare. For these industries, system-level complexity creates new EMI challenges as data speeds increase. Automotive. Let's take example of Automotive Ethernet interface, started with 100 megabit per second, then 1 gigabit per second, work on 10 gigabit per second interface. So this is something which introduces huge EMC problem directly at the car OEMs. So what we need to simulate in advance before ECU, electronic control units, is ending for the final test at car OEM system. We need to simulate emissions and immunity of automotive ECUs. 3D far-field patterns can be used to determine if the system is within EMC compliant limits. Multiphysics analysis with FEM solver tests for EM susceptibility. Consumer electronics. We can optimize antenna placement on PCBs to ensure data reliability in wireless transfers. We can simulate with human body models to ensure that 3D far-field patterns are within specific absorption rate limits. We can ensure EMC compliance before entering chamber testing. Healthcare industry. Simulate electronics in the human body and optimize wireless communications. Ensure medical electronic products meet strict Class A or B compliance standards. System-level modeling must advance with industry demands. So designers, they require new technologies for 3D electromagnetic compliance simulation. I've heard a lot of times from my customers that they just don't have a good path to full system simulation for EMI, so they put focus on an emphasis on prototypes or pre-compliance checks. So this is something that introducing simulation, it would help a lot to establish EMC design side predictive process for analysis of the EMC issues. As the outcome, of course, we would have a fewer expensive prototypes. Accelerated time to market requirements require physical prototype testing by replaced with a simulation. Test measurement accuracy is required from simulators. We need scalable computing solutions. So legacy tools with old architecture scale poorly and require multiple machines with terabytes of memory to provide any level of acceleration. Definitely, it's very important to have integration with implementation tools, because if we use only point tools, this requires painful extra steps to correct design problems. Accurate, timely, cost-effective solutions, that's something what is needed in the industry, versus inefficient simulations that take weeks to complete on expensive, dedicated hardware. Clarity 3D Transient Solver. It's giving this test measurement accuracy and extreme performance. this tool is capable for the massive parallel execution. So it's a multi-threaded, distributed processing, cloud-ready. It's having virtually unlimited capacity. Large system simulations can be addressed with as few as 8 cores and 1 GPU. Add more cores or GPUs for nearly linear scalability. No loss of accuracy. So with all this massive parallel execution, so accuracy is at the end guaranteed. So you can see on the right side that Clarity 3D Transient Solver is used as a global solver which can address very large problematics. So if we look at the PCB or IC package, look for the local fields creation, we can use a Clarity 3D finite element solver, but Clarity 3D FDTD Transient Solver is basically used as a global solver, which can definitely give you a good prediction on the far EM field, that EMC compliance can be checked, and that everything also on the near fields using Clarity 3D finite element can be checked properly. Using 3D FDTD solver, we can predict EMC and EMI problems associated with ECU designs, PCB plus mechanical chassis. We can solve for various EMC and EMI problems associated with devices operating in a complex environment, including chambers, PCB boards, and much more. I will give an example which is speaking about the optimizing the whole pattern for an ECU chassis using our 3D FDTD transient solver. So Clarity Transient Solver Simulator was used to optimize mechanical chassis. So first, step file of the mechanical chassis was imported inside of the Clarity Transient Solver Simulator. And after importing of the step file, so then each and every part of geometry should be associated with the proper material from our material library, which is describing electrical performance of each and every material defined in this system constellation PCB plus mechanical chassis. Here you can see a zoom which is showing mechanical holes pattern, which are originally placed there at the chassis. And what we will do in the first step, it will be to check the performance and what kind of the fields, at which frequency, critical frequency fields are leaking out through these mechanical holes. On this slide, I'm showing the way I'm creating rectangles at critical component positions. So it means I have imported step file also of the PCB. I can find each and every component critical position, and I can put a defined rectangle either at the PCB level, emulating the area of the critical signal switching, or at the component level, emulating electromagnetic fields which are leaking directly from that critical components. So what I'm doing here, I'm defining excitation electromagnetic field on this rectangle that I specified at a component of interest, emulating leakage, generating noise basically from that particular component. Then what I did, I basically introduced 6 rectangular surfaces around this mechanical chassis in order to generate electromagnetic fields on those rectangles. So those rectangles are basically used as a field output, and I just set field outputs on those 6 rectangles. So on this slide, you can see original pattern of mechanical holes, and this is something that I will call in the analysis so pattern 0. You can see that all holes are open, and this is something that we will try to exchange with the other patterns, because this is opening of the all holes it's good for the sake of thermal, but if there is any noise or fields leaking out of the chassis, so this is definitely the area where those fields can freely leak out of the chassis. So this is the example of pattern 1. So some of the holes are closed, so we have 3 lines of the open holes, but the holes on line 2 and 4, they're closed. This pattern is called the pattern number 1 in this analysis. So on this slide, I'm showing additional pattern. So now it's not so, we don't have such a uniform openings like in the previous slide. So we are just combining and creating specific patterns to see how this will affect leaking fields out of this chassis. And this is called in the analysis pattern number 2. So when I'm looking at this optimization of mechanical holes pattern at the chassis, so here you can see on this slide that I can choose the meshing with a 0.04 millimeter mesh, and then you can see how much elements I would have within one hole, or I can choose the meshing of 0.4 millimeter mesh. Still, I will have enough elements within a hole, but of course, with this kind of information, I will have much more detailed results. So for finer mesh usage, more memory and computational power will be needed. So GPU introduction is essential in this case. Let us take a look at the results for the original hole pattern, pattern 0. So we are measuring for all 3 pattern cases, E total at 6 gigahertz, okay? And scaling is completely the same for all 3 patterns that we can compare also visually about the differences with different pattern or openings of the mechanical holes. So mesh which was used is a 0.4 millimeter mesh. So you can see the field, so with the original mechanical hole openings, then we can compare that to the pattern number 1. You remember pattern number 1 was we have a stripes in the opening, so we have row 1, 3, and 5 open, but 2 and 4 they're closed. So here you can see that EMI is higher with the hole pattern 1 than with the original design. Okay, so we are measuring at 6 gigahertz. We have the same scaling, so that means we still have a stripe with the open holes, and we will see a hot spots in the leakage field along those stripes, and this is something which will be seen in this kind of the simulation. If we look at the hole pattern 2, so we can see that EMI is lower with hole pattern 2 compared to the other choices. But of course, here we closed some of the holes, and this will definitely affect the thermal, and this must be validated with thermal team that hole pattern is acceptable. So what we wanted to show with this simulation is that basically in advance you can work on the opening mechanical hole opening patterns in order to reduce field which will leak out of the chassis. And this kind of the work can be done in cooperation with thermal engineers, because they need holes for the sake of thermal. They need to cool down electronics inside of the chassis, but they sometimes or very often they don't think about the effects this could introduce on the leaking fields outside of the chassis. So that means with Clarity Transient 3D FDTD, this cooperation work with thermal team can be done successfully. Different mechanical hole opening patterns can be investigated, and in conjunction with the thermal team, at the end, we can converge on the final mechanical hole pattern opening. Now I will show example 2, which is basically showing full ECU simulations to validate compliance with EMI regulations. Here you can see also ECU inside of the mechanical chassis, and we have 3 fields of interest. So like in the previous example, we will create field outputs plane, which are sitting very close to the mechanical openings at the chassis. So we will create one here, very close to these openings. We'll create another field output rectangle close to these openings here, and we will create the third one close to these openings over there. So we will be capable to measure near fields here, and we will measure also far fields at different frequencies like 2 gigahertz, 10 gigahertz, and 20 gigahertz. Okay? So if we compare mesh of 2 millimeter versus 0.4 millimeter mesh, so we can basically see that with 2 millimeter mesh simulation can be very fast, basically taking 4.5 minutes in a 2-core laptop, and with a 0.4 millimeter mesh, it will be around 2 hours in a 72-core server. Let us discuss accuracy and performance trade-off. If we compare the results on the far field, looking at a 2 millimeter mesh, but just taking 4 minutes for the simulation, we are comparing those results to the 0.4 millimeter mesh results and simulation run of 2 hours. So we can see that basically in the far field, we see much more details now if we are using a finer mesh, of course, that we are seeing much more details in this case compared to the 2 millimeter mesh, which is shown here. So the conclusion would be that finer mesh is needed for much more details about the far field orientations, but 2 millimeter mesh can be used for the fast assessment of the system and in order to predict, so is there any particular problem with the far fields in this area? Accuracy performance trade-off, 2 millimeter mesh versus 0.4 millimeter mesh. So you can see a local fields at 10 gigahertz. Those are the near fields. So with a finer mesh of 0.4 millimeter, you can see a leakage through each and every hole respectively. And you can definitely make a judgment how big is the field, so leaking field, and you can compare this kind of the simulation to the measurement. Analysis summary. So Cadence Clarity Transient Solver used for the analysis of the ECU system to capture emissions leaking out of mechanical chassis at all critical frequencies. With a detailed mesh, critical frequency correlate very well with the measurement results. Less detailed mesh can be used for quick assessment, but detailed analysis requires computational power, eventually GPUs. The mechanical hole patterns creating leakage problems were simulated and optimized. Cadence Clarity Transient Solver can predict potential EMI problems of a complete ECU design, PCB and chassis. EMI engineers should closely work with thermal engineers to optimize mechanical holes patterns in the chassis. Cadence Clarity 3D Transient Solver, together with Celsius Thermal Solver, can help create an optimized system. Using GPUs to accelerate EMC analysis. GPU acceleration, and CUDA. Modern GPUs have evolved into highly parallel core systems, allowing very efficient manipulation of large blocks of data. Compute Unified Device Architecture CUDA is a parallel computing platform and API model created by NVIDIA. 3D FDTD is well suited for GPU due to its ability to segment the problem and parallelize the solve. We implement these GPU targeted functions in the 3D FDTD engine code to speed up the simulation. Inside Clarity 3D Transient Solver, using GPUs to accelerate EMC analysis. First, we'll start host code. Then copy input data from CPU memory to GPU memory. Then we will load GPU program device code and execute, caching data on chip for performance. At the end, copy results from GPU memory to CPU memory. So here you can see some benchmarking on the GPU server. So it's a Red Hat 7.6. So it's NVIDIA, Tesla, by 4 each, 5,120 cores. So you can see characteristic of CPU, CPU memory, GPU memory. And then if we compare GPU versus CPU case for very big cases, so we can see that simulation time used 2 CPUs and 40 cores can be 12.5 hours, and with 4 GPUs, we can basically simulate it in half an hour. So with 4 GPUs versus 40 cores of CPU is about 25x of speed up. Can you imagine if we have just a 10 times speed up of our ECU case just using the GPU? So that means instead of just introducing and analyzing, optimizing 3 whole patterns, we could do 30 different patterns using GPU for the same amount of time. So it's definitely crucial to use a GPU to speed up this kind of the 3D FDTD simulation using our Clarity tool. And now I will turn it over to Max from NVIDIA to speak in detail on GPU computing.
Hello, I'm glad to be collaborating with our ISV partner, Cadence Design Systems, supporting this presentation today. High-performance computing has transformed both the basic and applied sciences over the last few decades. Traditional high-performance computing domains like computational fluid dynamics and molecular dynamics have benefited profoundly from advances in hardware and software, and the impact has been felt in areas as diverse as drug discovery, weather forecasting, and manufacturing. More recently, artificial intelligence has been paired with HPC to enable high-accuracy model at low computational cost. Many breakthroughs in HPC today use NVIDIA hardware and software, and NVIDIA often collaborates with academic and industrial researchers to enable high-impact work. Much of the improvement in HPC performance over the last decade has come from massive parallelism. Limits on per-core processor performance have prompted many companies to increase the number of cores that they can fit on a chip, and NVIDIA has been a leader in this domain over the last 2 decades. Applications that can express large amounts of parallelism benefit from these newer processor architectures. In the paradigm of accelerated computing, a standard CPU handles program control flow and other serial parts of an application, and the parts of an application that can run in parallel are offloaded to an accelerator. This enables a substantial opportunity for improvement in application performance, though it does require developers to clearly identify and expose parallelism in their application. NVIDIA provides several convenient ways to target accelerated computing platforms. Of course, if you have a problem that uses standard math library interfaces, such as BLOS or LAPACK, NVIDIA provides GPU-Accelerated math libraries for drop-in acceleration, following the standard advice to use the vendor libraries where possible. If you need to adapt your C, Fortran, or Python source code to target GPUs, NVIDIA provides several programming models at different levels of abstraction. At the highest level are accelerated standard languages, for example, the use of C++17 parallel algorithms and do concurrent from Fortran 2008. Thus, using the NVIDIA HPC SDK, you can write ISO standard compliant code that is GPU accelerated. To enable further optimization in a portable way, we support OpenACC and OpenMP directives that allow you to indicate which loops should be accelerated by the compiler. And if you want to drop down close to the metal, you can use CUDA C++ or CUDA Fortran. In Python, we also now support Legate NumPy, which allows you to transparently accelerate NumPy operations across one or many GPUs. Many industrial HPC applications, and almost all of the top HPC applications in general, are now GPU accelerated. HPC is a full-stack problem. Using an HPC cluster efficiently means not just targeting the CPUs and GPUs effectively, but also the network. Ideally, your data will be resident on the GPUs for as long as possible, avoiding unnecessary round trips to and from the CPU. Essentially, all modern MPI implementations are now CUDA aware. This means that when using an MPI communication API, you can pass in a buffer pointing to memory resident on the GPU. Here, we are looking at an example where rank 0 is sending some data to rank n-1, and the send buffer and the receive buffer both point to GPU resident memory. For example, memory that was allocated with CUDA malloc. The implementation decides how to implement this operation most efficiently, ideally taking advantage of NVIDIA GPU Direct technology, as we'll discuss next. The NVIDIA HPC SDK includes HPCX, which is an optimized communication library including OpenMPI 4 and UCX, and we recommend this on NVIDIA accelerated platforms using InfiniBand for networking. The SDK also includes NVSHM and Nickel, which allow you to opt in to even higher performance, since they provide APIs that are compatible with asynchronous communication workloads on CUDA streams. And in the case of NVSHM, you can even send messages directly from within a GPU kernel. NVIDIA accelerated HPC servers rely on high-performance networking to augment the high-performance computing. Communication can quickly become a bottleneck in HPC calculations due to how fast the compute phase of the calculation completes when it is GPU accelerated. NVIDIA GPU Direct technology is what sits underneath high-level abstractions like CUDA-aware MPI. GPU Direct peer-to-peer communication is a technology that enables extremely high bandwidth and low latency communication between GPUs on the same server. NVIDIA's NVLink and NVSwitch technology result in several times higher throughput between peer GPUs than traditional PCIe connected servers. Additionally, these peer GPUs can directly access each other's memory space at low latency, enabling solution of very large problems. Meanwhile, when communicating between GPUs on different servers, a traditional CUDA-aware MPI implementation might be to stage a copy of the data to the CPU, send a standard message over the network card through the network to the remote CPU, and then down to the remote GPU. When using InfiniBand network adapters, however, NVIDIA GPU Direct RDMA technology enables high throughput and low latency messaging by skipping the staging of the data to and from the CPUs by having the GPU communicate directly to the InfiniBand adapter. Importantly, this can all be done transparently to the developer and the user. MPI implementations like OpenMPI will automatically use this messaging paths when it is available and judged to be efficient. This enables much better ability to strong-scale GPU workloads. A good example of what is possible with large-scale industrial HPC is presented at NVIDIA's GTC conference of 2020. The Summit supercomputer at Oak Ridge National Laboratory in Tennessee has 27,000 NVIDIA V100 GPUs that can be used for complex problems. Computational fluid dynamics is a classic use case for such a supercomputer, and Numeka's CFD code enables a particular CFD test case with over 500 million degrees of freedom, with an eye towards scaling up to over 1 billion degrees of freedom running for up to 1 million time steps. A use case that would take half a year using only the CPUs on 32 nodes could be done in only a week and a half when additionally using the GPUs. And because Summit has thousands of GPU-accelerated nodes, the same problem could be solved in as little as a day by going to larger scale. Problems that were once considered hero calculations on standard CPU nodes can approach being normal workday jobs when taking advantage of GPU acceleration. Cadence also takes advantage of GPU acceleration for Allegro. While many aspects of the system design domain, such as electromagnetic field simulation, are classic parallel HPC problems that can benefit from using GPUs, GPUs shine in other ways too. Allegro uses GPUs for smoothly and quickly rendering the board, enabling faster iteration during the design process. Additionally, machine learning calculations, themselves being a deeply parallel problem, can be done at high performance and with strong power efficiency on NVIDIA GPUs, and Allegro uses this quality of NVIDIA's GPUs to enable placement and routing on the board. NVIDIA technology makes it quite easy to use GPUs for machine learning problems. The popular deep learning frameworks like TensorFlow and PyTorch are GPU accelerated out of the box. NVIDIA provides high-performance Docker containers on ngc.nvidia.com with optimized implementations of these frameworks for both machine learning training and inference. With these reference implementations, you can get both best-in-class performance and extreme simplicity and ease of use, as well as the guarantee of reproducibility of your work. I mentioned earlier that HPC is a full-stack problem. NVIDIA is committed to this vision and supports all aspects of workstation and data center HPC and AI usage. NVIDIA Quadro GPUs enable state-of-the-art calculations on high-performance workstations for rendering workloads, data science calculations, and generally problems requiring large amounts of memory. NVIDIA worked closely with our partners in the consumer gaming and enterprise workstation markets to enable excellent system design. And NVIDIA also offers the DGX Station A100 for the most demanding AI workloads in a workstation environment that fits under your desk. NVIDIA's data center GPUs, such as the Ampere A100 GPU, are the most powerful accelerators available for server-class high-performance computing and AI. NVIDIA's OEM partners in the enterprise server space incorporate NVIDIA GPUs into both their standard and high-end designs, and NVIDIA collaborates deeply with these OEMs to ensure that the end user will have a great experience. All NVIDIA certified server designs have been carefully validated to ensure compatibility with GPU-Accelerated HPC and AI workloads. In addition to our partner offerings, NVIDIA DGX SuperPod is an AI supercomputer solution for organizations that want a known good reference architecture that enables the best possible AI performance. Right now, we're in the midst of an explosion of use cases for HPC. Extreme scale HPC is no longer the domain of only government labs. Rather, industry can take advantage of HPC to solve many important classes of problems. HPC systems are regularly finding new uses. For example, the COVID-19 pandemic resulted in a great demand for HPC systems in areas like molecular dynamics and drug discovery. Particularly, a trend that is worth paying attention to is the convergence of HPC and AI. Many HPC problems, especially in the industry space, are expensive to compute. Even when accounting for the acceleration that GPUs make available, it's natural for researchers, engineers, and designers to take the logical next step and solve problems with even more computational power than before, usually to run simulations for a longer time or at higher fidelity. But it's often not feasible when going through the design process to run your biggest simulation every time you want to experiment with a new design. Artificial intelligence enables surrogate models of these HPC calculations that can be cheaply and efficiently evaluated. These surrogate models are trained directly on the HPC calculations. And today, we see a rise of physics-informed neural networks that enforce the constraints of the physical problem directly in the neural network, resulting in higher accuracy and more confidence that the solution produced by the neural network respects the constraints that you want to enforce. These AI models can be easily deployed on the NVIDIA platform. NVIDIA continues to innovate on this platform in both the hardware and software space, and we look forward to collaborating with you for many years to come. I'd like to thank Cadence for inviting me, and I'll pass it back to Surjan for the remainder of the talk.
Thank you, Max. Clarity 3D Transient Solver 3D System Modeling. So board-level EMI contributors code with Cadence Sigrity in design analysis. So that means emissions from the board you can capture either with the Cadence Sigrity Power Side tool. It can be also done using a Clarity 3D Finite Element Solver, looking directly at the PCB level. But system level sign-off, it's done with Clarity 3D Transient Solver. So it's industry's most comprehensive solution for EMC, emissions, and immunity. Clarity 3D Transient Solver summary. Accelerates products to market with fast and accurate 3D simulation results that enable EMI compliance for emissions and immunity. Reads all design platform data and is integrated with Cadence chip, package, and PCB design platforms. Clears path to full system-level simulation. Thank you for attending.